My name is Craig Quadrado. I'm with WIS Janney Elsner and Associates here in San Antonio. So I've been here for about 8 months working with this company. Prior to that, for the last 25 years, I was an Army engineer working all across the world doing Army construction, education, and really enjoying it. And did a lot of research in lateral torsional buckling, so it's my pleasure to present part of the presentation this morning. And I will let my co-presenter introduce himself as well.
My name is Perry Green. Right now, for the last 6 years, I've been working for Bechtel Power Corporation doing nuclear structures. I thought I had gotten out of that after 12 years of nuclear structures back in the late 70s and 80s. And that's when I realized I needed to go back to school to learn some more things about the behavior of structures and steel, which I did. And my research work was on the flexural behavior of members. And so that sort of fits into this talk also. And there was a stint, if you might remember, some of you, that I was also the technical director at the Steel Joist Institute for 6 years. So if any of you work with little things like joists, you might have had to run into contact with me during that time. So, and I'll be doing the middle part of this lecture.
Yeah, so I get to bookend Perry, but I think what Perry was really trying to tell us is if you have a really tough question at the end of the session, Perry will be answering the question a little bit. Again, the PDH code for this session is 14624, so please go ahead and use that, and we'll announce that again also at the end of the session. So we've already done the introductions. Very happy to be with you here this morning. The agenda will follow. It looks like this, a little bit of a smattering. For those of you that might have attended this session in years past, given by others, I know in the pre-program it was Ron Zemian. I know I'm a much shorter and not as good-looking version of Ron, but hopefully we'll fill his shoes well here. We'll start with a quick introduction, just get some of the basics down. Then we will go into some fully plastic behavior discussion by Perry. Then we'll get into the basic lateral torsional buckling, at least the elastic equation derivation. And then we'll talk about deviations from that basic case, specifically how we handle inelasticity, load conditions, warping, and restraint. So we'll run everything from the AISC code on into some of the current research and other resources that you may not be aware of in terms of lateral torsional buckling. And then, of course, we'll conclude with a summary and some final thoughts. So let's get on with it. Start with our introduction. What is lateral torsional buckling? Where we're really going to be living, if we look at the chapter F out of AISC 360-16, we'll be living right here. We'll start up there with chapter F2, and we'll dip down a little bit into section F3 as well. We'll really limit today's talk to doubly symmetric shapes bent about their strong axis. For the limit states of yielding, lateral torsional buckling, and flange local buckling, we'll talk about a little bit as well. And at the end, we'll give you a whole host of other resources that'll go deeper into each of these topics and cover some additional topics as well. All right, so let's talk about the AISC beam curve and the basic case. I'm sure most of us have all seen this, the beam curve. And, you know, these are problems that we have that occur all the time. All I had to do was one quick little Google search and find July 20, 2015, this girder buckling failure out of Edmonton, Canada, right out of the Edmonton Sun. And here they say the lack of bracing was blamed for the buckling of these bridge girders. We'll talk a little bit about that. Maybe it's not the lack of bracing. Maybe it was something else. So if we zoom in, we can see that nice buckled shape, right, that none of us want to see on the job site when we wake up in the morning and go out there, right? Or get a call to go out in the middle of the night. So what is lateral torsional buckling? Really, just in its simplest form, it's a geometric instability, right? So the properties that govern the instability really do have to do with the geometry of the problem, and of course, that limits the loading that we see. It's a combination of lateral translation, you know, for our horizontal members, lateral translation out to the side, and then cross-section twist together. And why do we see this sort of behavior? Well, if you think about your stresses in your beam that's bending or that beam that's smiling at you there, you're going to have compression on the top and tension at the bottom. And what happens with a member in compression? What does it want to do? Yeah, one of the possibilities is it wants to buckle. And of course, the top flange there would buckle, and it kind of drags along the bottom flange with it, causing that twist. And we can see here in the next slide just three different views. If we're looking at our beam from the elevation view, it looks great. It looks like it's smiling at us. But if we look at the top view, we might start to see that top flange start to bend. Of course, the bottom flange not shown in that picture would be underneath it, and that would show the twist and the lateral translation that you see at section A. So that's what it is. This is how AISC describes that behavior in terms of nominal moment strength, right? So if we plot that nominal moment strength on a vertical axis and we plot an unbraced length on the horizontal axis, we see that the primary variable for the moment strength for a given cross-section is that unbraced length. All right, a couple of examples here as we go. This is a great picture from Don White at Georgia Tech. Shows that in elastic lateral torsional buckling, we get that good buckled shape, but if we remove that load, what's going to happen? Our beam will pop back into its original undeformed position. I've seen this many times in the laboratory. It's quite amazing sometimes to get that kind of deflection, and then watch it, once the load is removed, pop back into shape. Here's another example of a different sort of lateral torsional buckling behavior. This some picture I dug up from the Army. I'm not quite sure. I think this might be in Bosnia or Kosovo. It's somewhere. Somebody took it. I don't know who, but it's a great example of something heavy went over that bridge. Maybe a tank, maybe some kind of heavy construction equipment, and bent those girders underneath the bridge. Now the load's been removed. We've got the permanent deformation. That's the classic definition of our inelastic lateral torsional buckling. And then finally, if we have the correct unbraced length, we can actually achieve a full plastic moment capacity of our cross-section, which we'll talk about in just a second. Right? So these three behaviors are all described based on our unbraced length. So the big question really amounts to is, where do you want to be on the curve? Do you want to be in the elastic region, the inelastic lateral torsional buckling region, or the plastic region? Well, the AISC code will tell you on page 16.1-323 that being able to use the full plastic moment capacity represents the optimum use of the steel. But of course, I'm here to tell you that sometimes yes and sometimes no, right? If we just look at that one cross section and we just consider the element as an individual, maybe this is true. But, based on the fact that sometimes we don't want to be in the inelastic range and other times there are other efficiencies across entire systems, maybe this doesn't represent for our project the best place to be. So we'll talk about all three of these regions as we move through the talk here. So what does it mean to be in full yielding? Well, if we look at our cross-section in a little bit different way, and we take our beam and we bend it up through a rotation theta with a moment m, and we plot those two, we'll get a curve that looks something like this, and we'll apply that rotation, and somewhere below yield, we'll have our cross-section completely below our yield stress of our material. If we continue to bend that beam up and increase that rotation theta, we'll pass through a region where we start to see some plastification, right? So now the flange tips here have now plastified. So we've got a core here, web, and some of the flange in this particular case that's elastic, and then the top and bottom of our flanges have exceeded their elastic range. And then finally, as we continue, if we continue to bend that member, we will eventually reach a place, at least theoretically, where we have our full cross-section has achieved its yield stress. And it's typical to ignore other material properties such as strain hardening and all that in our basic analyses. So we're not going all the way up that stress strain curve and looking at strain hardening in this talk, and neither does the AISC code, at least in this chapter. So where do you want to be? The next question is, how do you actually get there, right? And that's where the fun comes in. First, just a quick definition of unbraced length for those that may not be familiar with it. That's the length between the points that are either braced against lateral displacement of the compression flange or braced against twist of the cross section. And really, what we're really getting down to here is, in the primary, you have to stop the twist of the cross-section. If you can do that by bracing the top compression flange, that's great. But if you want to be assured that you have a good brace, you're going to have to stop the twist of the cross-section, right? And of course, designers control the unbraced length via effective bracing. Some examples of that, here's a skewed steel girder bridge being erected up in Lubbock, Texas, and we see the good cross frames in there. Our unbraced length would just be the distance between those cross frames. For those of us that like buildings, just imagine that decking taken off. We could kind of debate as to whether the decking braces that girder continuously or not, but if that decking isn't there during erection, our unbraced length for that girder would be the distance between the two beams which are providing the bracing or the resistance to twist that we need to have effective bracing. So what does effective bracing do for us? Well, if we have between our supports, whatever those happen to be, bridge abutments or between two columns in a building, right? We start out here with an unbraced length way out here to the right that would put us in this elastic lateral torsional buckling range. Of course, if we provide bracing, we might be able to shorten that unbraced length up down here into this region, which would then get us into our full plastic moment capacity region, right? Of course, the key there is effective bracing, right? Effective bracing, it's going to control the twist of the cross section. It's not going to be connected near the shear center of the shape either, right? Because if I connect a brace, just a single brace at the shear center, am I controlling twist? No, I'm not providing any restraining moment to control twist in the cross section. And here's a big one as well. It's not a point of inflection. I know kind of growing up around engineers, sometimes, they would think, oh, if I have reverse curvature in my beam or girder, then I can take those points of inflections as brace points. But the key there is, am I controlling twist at that point? No, we're not. So do not consider points of inflection brace points as well. All right, so I'm not going to go into how to design your bracing. You can read about that in AIC Commentary Appendix 6.3, and we happen to have a very special treat this year here at the NASCC. Todd Helwig, who will be giving the T.R. Higgins lecture tomorrow at 2:15, his lecture is on effective bracing for columns and beams. So if you're interested in, okay, how do I design this bracing and what are some of the things I need to know to do that, please attend that lecture. You'll be very pleased with what Todd has to put out. Now, back to our picture. We see that the nice, nice to some of us, buckled shape. And if you look very closely, you'll see that those braces have buckled, right? So maybe it wasn't a lack of bracing that allowed these girders to buckle, but it was just a lack of effective bracing that allowed these girders to buckle. Right? Those braces look pretty slender to me. All right, but now we've got to go a little bit deeper, right? Effective bracing still might not be enough to get you into that full plastic range, right? So there's a problem. As we start to bend that girder up, we might actually start to put enough stresses in the flanges themselves to where they'll buckle before the entire cross-section, right? So if we consider an I shape made up of 5 different plates, the web, and 4 half flanges as individual plates, those plates that are in compression, if I'm just kind of a standard beam, those top plates in that case, they may also buckle before the cross-section. And this is all governed by the width to thickness ratio of those plates, right? The width to thickness of the web would be considered the height of the web over the thickness, of course, and more importantly for our rolled shapes, we would consider the flange slenderness to be the width of the half flange over the thickness. So AISC has a nice chart, and many of my undergrad students would confuse this chart with the beam buckling curve because it looks a lot alike, right? But if you'll notice down here, we're not plotting L sub B, right? We're plotting the slenderness of the flange, that BF over 2TF. But we still have the same sort of behavior in the individual flange plates as we do with the entire cross-section. We have a slender elastic flange local buckling, we have an inelastic flange local buckling region, and we have a fully plastic flange local buckling. So not only do we have to meet the bracing requirements, we also have to meet the flange slenderness requirements here. 0.38 Young's modulus over the yield stress of our material. We have to be less than that to actually achieve our full plastic moment capacity. What does that look like on our graph? Well, if we've got our effective bracing applied to be down in there in the plastic moment range, but we fail to have a flange that is stocky enough to be compact, our strength is going to drop some, right? It's going to be a little bit less. And then, of course, if we have even a more slender flange, our strength might be down here, right? A more slender flange. So here's a good example of that. And now I will tell you that full plastic capacity of beam typically comes with some flange local buckling as well. Usually we're getting the stresses high enough. And that's what we see in this picture. Yeah, we've yielded the full cross section, but we've also got a great example of flange local buckling going on here as well in this cross section. And that's what that failure would look like. So how do we live with the possibility of flange local buckling? Well, some options. Notice I've crossed a couple off because they're really probably not going to do what you want them to do, right? We can increase Young's modulus. But of course, if I'm increasing Young's modulus, what am I really doing? I'm changing the material, right? Well, that might be appropriate for your application, but typically not in our field, right? We're going to stick with steel, so we're not going to be able to do that. Maybe we could decrease the yield stress, right? That would favorably impact my slenderness. But what else am I affecting if I decrease that yield stress in my material? No, I'm also decreasing the strength of my material. So that probably won't get you what you want, right? Well, we can also change the geometry of the plates, right? We could get some thicker flange plates, and that might work for us. Or the bottom line is we might just live with it, right? Maybe we're not so concerned with flange local buckling in that particular region. And oh, by the way, maybe the lowered strength is okay for that region of loading, and we don't need more strength, and it's more efficient to stick with that particular cross-section in the entire structure instead of changing cross-sections for that. So if you want to live with it, you can certainly calculate the reduced strength using section F43, paragraphs B and C. So it's not necessarily the end of the world if you have a section that's subject to flange local buckling. You can work for it. The nice thing here are our producers have really, almost gotten rid of flange local buckling in all our shapes, except for the shapes that you see listed on page 16.147. And if you're wondering if I'm using the design aids in the manual and I happen to have one of these shapes, are those flexural strengths reduced for the possibility of flange local buckling? Yes, they are. And you can read about that in the individual design aid descriptions in the manual. So that's all baked into the manual for you. But just so that you know, as a designer or somebody that might be fabricating or erecting, those are the shapes that might be susceptible to flange local buckling. All right, so with that, if we can, have our individual plates, the appropriate slenderness, and we can have a good effective bracing to get us into the plastic range, we can count on that fully plastic behavior. And that's where Perry will come up and talk to us about his depth of knowledge and research in this area.
I do think I want to go back here for a minute. That note at the bottom that we sort of, at least in the world that I now live in, nuclear structures, I look at plates that are not typically A572 grade 50. Some got substituted out as A572 grade 60, some as grade 65. They want to actually look at within the specification for the 2022 spec. And other producers, when you walk through the exhibit hall, there are materials down there that, there are manufacturers that will roll you 100 KSI plate. And in the bridge world, they look at that. But what is that doing in your equation? Where is the FY? So the FY is in the denominator. So you really, if you're always thinking 50 grade materials, A992, that's what you have, and that all works fine. But as soon as someone says, can we use a different material or a different yield strength? Now you have to not just use the values that are in the tables in the manual, you probably have to use the spec and calculate your slenderness values. So I will leave you with that little tidbit before we go on. So back a couple years ago when I was getting my PhD, I was asked to look at, for a new material that was being developed for the Navy, which was called HSLA 80, high strength low alloy steel, 80 KSI yield, and had about 100 KSI ultimate, okay, because they were looking at building their structures, mostly all floating in water, out of this material. So we wanted to understand what were the changes that we would be seeing if we went to an 80 KSI steel. Essentially, that was a nice project, but what it really led into not that many years later is your HPS 70W for bridges. Then they developed 100W, and then I think they finally rolled back down and developed the 50W. And the W stands for weldable. Okay? So in the bridge world, there are 3 steels that are used. I don't know whether it's primarily now. But the nice part about the work that's done when you do elastic lateral torsional buckling in an experiment and you take the load off, guess what? You don't have to replace any of your instruments. You might have to make sure that they're all still located there. When you actually go and do this behavior, everything is done. And you have to replace everything or take everything off. So all your strain gauges, all your all that measurement has to come off and get put on the next experiment. So what we were looking at is to develop that full plastic behavior, to develop the rotation capacity that we need. And this really is both for non-seismic, or I'll say monotonic loading, or for seismic loading or cyclic loading. What is that behavior and what are those differences that we really need to have a full understanding? Because you realize everything in this code in 360 is really based on, I'll say, static or quasi-statically loaded structures. When you get beyond, then you go into 341 for AISC. So the first thing I want to get into is the definition of rotation capacity. And there's a simple definition of that rotation capacity. R is the ultimate rotation, the end rotation, if I have a simply supported beam, we're just looking at that end rotation, to the rotation that we achieve when we get to the full plastic moment, MP. So that is the theta P. So within the glossary of 360.16, you'll find this definition. Rotation capacity, it's the incremental angular rotation defined as the ratio of the inelastic rotation attained at the idealized elastic rotation at first yield prior to significant load shedding. So somehow that definition and that definition have a little bit of delta in them when I see that, because this is talking about first yield and I'm talking about theta P at when I reach the full plastic moment. Two other definitions I'll just put up here quickly are theta inelastic is just removing the elastic portion out of that. And so we can compare things on a one-to-one basis when we look at the experiments that were done. And also displacement ductility. You find this more in looking at if I'm loading a structure and I really don't want to deal with the end rotations, but I want to look at what is that ductility that I achieve. If I've got a point load on a beam, what is that displacement? So if I take the same definition essentially for the end rotation, I can do it similarly here using delta U over delta P. Test looks pretty simple. Okay, there's your beam. It was placed on a reaction beam. It was placed in a 600 kip load testing machine. There are your supports. If we idealize our test, we're really doing a very statically indeterminate test. There are rollers. You'll actually see in a lot of pictures, they'll do a pin and a roller, and I sort of have a little bit of heartburn with that. These were two rollers in saddle plates. So literally what happens is when that beam starts to get load and rotate, those rollers will start to roll up those saddles and then they will roll back, essentially roll back down. And it'll be that slip because they are very, the machine, and they're also greased rollers. So we could actually take those rollers, if we scribe vertical lines at the end, we can actually look at those where they wind up and how much they've rotated. So there is the brace spacing, and again, this goes back to the definitions. Everything that was done in this presentation, which I won't date the age of this, is all done in SI units, because there was a time when we thought we were going to move to SI. And AISC published those nice, pretty orange books. Who has a set of orange books? It also says how long ago you've been coming to these conferences, because there was a year where AISC said, we're getting rid of all of these. They put them where all the magazines are for free to pick up downstairs. They just piled stacks of the manuals and free just to clear out their warehouse. It cost them too much to store. So there is the brace spacing for this beam, which is, I can't do this math anymore. Okay, this is a fairly 12-foot long, these beams. Gosh, I should have thought about this. So the brace spacing that's here is to ensure that I have my brace spacing close enough. And if you saw in the pictures that Craig showed, we have LP, we have LR along that unbraced length. And there was actually an earlier requirement within AISC that if you were doing plastic design, there was something called LPD. For the more experienced people in the audience, you might remember a term LPD. And LPD said you have to have a brace spacing that's actually less than LP to be able to do plastic design. So the brace spacing in these experiments was actually done to LPD to ensure that we would not get
lateral torsional buckling before we achieved full plastic loading on the beam and seeing how far we could carry that to determine what the rotation capacity would be in the experiments. So here's one particular experiment that I'm going to walk you through, and hopefully you can see in the back these pictures. So the first picture, we're at about 90% of MP, our rotation is 0.96 of MP, and there is a normalized, God, I can't even read it, it's so small. It is the normalized moment over the normalized average end rotation. And that's what all these plots are. So really it's looking at the experimental line going up. So the second picture is we're at 1.126 of MP and a rotation of 2.42 MP. And you see that we've actually gotten above MP. So part of that, but you also see in the picture, if you can, I have this pointer. We're developing some local buckling here. But we're still carrying load. We're still up here. We're still able to put on maybe a little bit more load before this beam wants to give up. So let's go to the third picture. Now we're at 1.04 MP. We've got about 4 theta P in rotation already. Here's that local buckle, how much it has grown. And we're just getting back to essentially the idealized MP of that specimen. And we can finally get near the end. And there's the beam when it's done. And there is that local buckle of those flanges. And it was funny, Dr. Ostapenko, who taught at Lehigh for his life and a mentor, he took a picture of that and he signed it and he handed it to me and he said to me, I can do that every day mathematically, but I've never seen it done in the laboratory. And why was that so poignant when he said that to me? What typically happens with our loading, with our specimens, everything, it's not ideal. So if the load is just a little bit shifted, if the specimen is a little bit not perfectly straight, you're always going to get, as you saw in that earlier picture, which was again one of my tests, you would get one flange up and one flange down. But you would get the local buckles, but they would always be in opposite directions, not this way. So because of all this nice instrumentation that was put on here, we could actually get, and here is your rotation. Here's that plastic hinge. We're getting the, if we calculate, these were rotation meters, and we calculate the curvature. So if we're looking at moment curvature, that curvature is going to infinity here. There is your plastic hinge that occurred in that beam. So if you have not seen a plastic hinge up close and personal, there is one. So to understand how good behavior is, we'll also get into some bad behavior or less behavior of members. And we wound up testing 13 specimens, and we're going to point out these two, and I want to sort of hit myself because I didn't bring the pictures of specimen 4, and to show you the difference between 4 and 4A, we had to rebuild 4 for a reason. Why do you think that reason was? Look over here. And this is really the only column of numbers that we really want to look at. We got a rotation capacity of 1.2 here. But when we redid the test, it was close to 3, which is what we were looking for when we designed that specimen. What did it have to do with? What failed in the test? What did the beam look like when it was laterally torsionally buckling because the bracing was not effective? The bracing system that I had designed could carry something like 10 kips of flange force or maybe 15 kips of flange force. Well, these beams were, and unfortunately we did not instrument the braces, but I must have had more brace force than that because I buckled a brace. As that beam wants to go, there's a lot of force in that beam. And the beam buckled laterally torsionally, inelastically, and so we did not achieve the rotation capacity, so we said we need to rebuild the specimen. So all this is just a column of numbers here. And before we go on to that is, it's really easy to push a beam till it achieves that load deflection, load rotation curve, whatever you want to call it. But if you want to do this same beam cyclically, or at least quasi-cyclically or quasi-statically, now we are going to push and pull on that beam. So what we have to do is, the experiment gets a lot more difficult. Why do you think we needed these big slotted end fixtures here? Do you think the length of the beam is the same length it was when it ended with the local buckling? That beam's going to shorten. Do we know how much it's going to shorten? Well, we've never measured it before because no one ever really thought about it. It's really simpler to do this experiment by taking half the length of the beam, welding it to an end plate, and pushing on the cantilever end. But you're really doing a connection test and not a beam test. So we developed this system to do simply supported beams. Now here's the bracing because, again, it's a moment gradient test, right? So our moment gradient, I'm only really interested in that part that is going to see the significant MP, which is near the braces. So I only needed 2 braces for this test. But what also happens in the cross-section vertically during the test? It wants to slightly axially shorten. I didn't have to worry about that when I'm just pushing on a beam. But when I'm going to push and pull, I can't have any slip in my fixturing. So the rollers wound up being placed here and pre-tensioned with these plates. So we had to literally pre-tension the fixture on there. So as that strain, axial strain in the web was increasing and it was getting shorter, we had to make sure that that fixture stayed in place. And here again, the values, these were tests 10, 11, and 12, and there are the rotation capacities from those tests. What we were really looking at, and I hope it's on the next slide, and then we'll come back. These 2 definitions, I don't know whether you've read them, but please take a moment and read both of them. This is what you've been told as a definition. Compact section, section capable of developing a full plastic stress distribution and possessing a rotation capacity of approximately 3 before the onset of local buckling. Okay? It's been in the code in similar forms for 20, 30 years, okay? But probably never defined or never demonstrated to you what that really means. And where do you need rotation capacity? Do you need it in a statically loaded structure? You need it in a structure that you're doing seismic design, right? So really, this was meant for when my beam is undergoing cyclic movement, okay, during an earthquake. That's where you need that rotation capacity of 3, not monotonically, okay? So now what we've done is we did the monotonic test, and now we want to compare the same beam design monotonically to the beam design cyclically. And where are we at? Again, our slenderness limits, if we look at back in the day, and this is done in megapascal square root, right? Because how many people remember 65 over the square root of Fy? Okay, let's see the more experienced people. 65 over the square root of Fy, that's what this value is. But that 65 contains the modulus of elasticity embedded in it. Okay, I have this issue right now with the design authority that I am working, actually, I review papers from the design authority, but I represent the owner. I'm working at Vogtle Nuclear Power Plant, which is under construction right now. And the problem was they did their slenderness calculations, and we're using old codes. We're using the nuclear code N690 1994, which is really the sister code to the infamous ASD Green Book, or the 9th edition. Okay? And so in the 9th edition, it's 65 over the square root of Fy. In your current edition, whether it's 2005, 2010, 2016, it's 0.38 times the square root of E over Fy, because we put the E back in. And there are several reasons to make sure that you know that there's 2 things that affect your slenderness. It's E and it's Fy. Again, my materials are not all carbon steels, and my yields are not all A992. So I get both ends. And there's a third part that I would like you to take away from this. Everything in your code is essentially ambient temperature. How many of you have ever dealt with something that you've designed that has 200, 250, 300 degree temperature because you're doing an industrial building? There's some piece of equipment or a tank or something that's hot, okay? And you're designing a support for it. When you consider these equations, again, now if you look at the fire appendix in the latest code, you can actually use those tables not just for fire, but you can use them for elevated temperature. It also affects slenderness. So these are some of the takeaways, probably more important than anything else, is E is really ambient temperature, FYs are ambient temperature, and carbon steel. So when we look at these values, these are what we were trying to achieve in our tests, and they're plots that are coming up, so we'll just get to the plots. So we laid out all the test results. So what we had were, the first two tests we did was more for fun. We varied the flange thicknesses. We did one that had, the first test had a 1-inch thick compression flange, 1/2-inch thick tension flange, and then we flipped it over. And if you really want to know how drastically the behavior is between those two, I think I didn't even put them in these graphs. I left specimens 1 and 2 out because they were unsymmetric. So we'll start with 3 through 12. And what we really want to look at is this behavior, okay, to have a good understanding when you get into these ranges. So we're plotting the rotation capacity here and normalized flange slenderness here. So the numbers really don't matter. It's really the trends of the curves. So we're looking at if I have a member that goes, that's a compact section that goes to a non-compact flange. So these were the same two specimens, same type of loading, and the only thing we changed was the geometry. I get a reduction in rotation capacity by making the flanges more slender. And I observe that maybe greater with a higher strength material. And look where I am. Here's that rotation capacity of 3 line. This is where I was at when I did the tests with cyclic moment gradient loading. When we look at, and I'm calling it ultra compact to compact, because we really went even a lot closer than, you know, if I look at that value that I calculate, that lambda p, and I get it something, let's say, half of lambda p. So I've calculated something that's very, very stocky. And I look at those. Now I go, and these tests were done with a uniform load. So we actually took a section of the beam. We did 3rd point loading in a series of the tests too. I only showed you the monotonic, the moment gradient, but we also did where we got a section of the beam that is uniform moment. And these were the uniform moment tests here. And you see with those tests, again, as I get more slender, I'm getting a reduction in rotation capacity. And again, here's with comparison with 2A36 steel members and then with my HSLA members. Okay. Some of the takeaways here are that what rotation capacity do I need if I was doing a monotonic test? It's probably almost on the order of 3 times that. If I had a rotation capacity of 8 or 9, more than likely if I'm in a seismic or cyclic type testing where that rotation capacity of 3 means something. And we've done this. We've taken our curves and we've taken the cyclic curves and literally fit over, like a backbone curve would be the monotonic test over the cyclic test to see all this behavior. I think this is the last one, where again, where we're at relative to the limits that are in the specification for web slenderness and for flange slenderness, it says that things are pretty good with where we're at, but when we are looking to go to higher strength materials, we're going to have some issues that we're going to need to address. And again, here's that same curve that Craig showed in a little bit different form. Essentially, I put it all together. This could be flange local buckling or web local buckling, or my MP. You know, in this range, I should get MP. And here's that LPD value, and there was that equation that used to be in the specification for LPD. It still shows up in the commentary in a figure, but they took the definition away. Or I think the definition of LPD is still in the definitions, but it's not anywhere within the body of the spec or commentary now. I'll look. In the 16. Okay. I don't think I saw the equation, but we'll look. I trust you. What we learned, and I think most of what's here is I've already stated, there's less rotation capacity available for higher yield strength steel members than A36. Now we've already moved up to 50 grade materials. Okay, so if you think about what we were doing and where now our baseline of materials at 50 KSI, probably we're okay, but how much further can we go before we really have to start adjusting or looking at our flange slenderness limits, our web slenderness limits, what is compact, non-compact, things like that. If I do a uniform moment test, the one thing with the difference between a uniform moment test and a moment gradient test is once I reach MP, it's over a length of beam. And I can't really get any more capacity in that member. What happens is in a moment gradient test with a point load is it's that spread of plasticity along the flange as I keep increasing the load. So that's why when that plastic hinge forms, I'm still spreading plasticity to a point. And that's why I can get to some value above MP in a moment gradient test versus a uniform moment. And again, cyclic moment gradient loading reduces the rotation capacity of the steel flexural member significantly. All of this was then, so there were all the experiments done. Then there was analytical modeling done of all the experiments, and to fill in the gaps that we didn't have from the experiments, we did a parametric study to see all of that behavior. So I think we're done with that part of that to me was the funner part than the math. So we can probably go through the math fairly quickly, can't we? Where we go to 8:30, 9:30. Oh, we have plenty of time. All right. I can go slow and you can all go to sleep. We could dim the lights now. So we're going to wipe the slate clean and rebuild the curve. We're going to look at this math. So that's the easy part, MP. That's where we would like to be, but how many times do we say is this is the critical beam in our design and we're going to use that same beam so the fabrication gets easier? So not every beam is ever going to see that full load. You know, so really where do you need to be on the vertical axis? Well, you have one critical beam member that you need to design and then you sort of replicate for your others and probably the rest is okay by inspection. So how do we get there? And no matter what we do, we can never get MN greater than MP for a given cross section. Well, you can, but it's in an ideal case, it's in a laboratory. And one of the things when you do a test, was I really doing the test by applying load? How many people think I did the test by applying load with that load machine? No, I really applied a displacement and from the load cell got the load. Okay? So that's why in the laboratory you see tests that can do all that and get you way out into that inelastic plastic region. If I was putting steel blocks on that beam, when it reaches a critical instability, it's gone. The load is there. So in the laboratory we sort of, I don't want to say we trick you, but we're really doing everything under displacement control and measuring the load that we get. I did one test when I was teaching at the University of Florida. I was there for a few years. And I had a student, we were testing a roof for uplift. And how was I going to do the test? Well, we built this nice roof. It was wood trusses, everything was scale. And I said, do not do the test. I was going away, coming back, and then we do the test. We were going to turn the roof over. We wanted to do a uniform uplift, but the simplest way, we figured we had plenty of sand in Florida. We were going to load it with sand. And he did the test before I got back. And guess where the test was when I got back to the lab? On the floor. Because once you've done and something's going wrong, you can't recover unless you stop and quickly remove some of that load. Okay? So more times than not, that it is clearly, we do things very safely under a displacement control situation. All right. So our initial assumptions, any of you in the short course on Tuesday? You are. Okay, you can go to sleep now. You will see some similar slides. I have to thank Ron for those, but we were not going to type all those differential equations back. So these are the basic assumptions to get to the equation that you use in the specification. Okay, only prismatic members, so our cross-section is constant. Only major axis bending occurs before buckling. Only linear elastic behavior, so our E is constant. Only uniform moment distribution loading. The only support conditions at the member ends, and they're frictionless. So no vertical or horizontal translation, no longitudinal rotation, and free to warp. So here's that beam, and I finally realized the difference between my experiments because I did not put braces at the ends where you see braces here. But what did I have welded on my specimens? There were vertical stiffeners, flange to flange, on my specimen. So essentially, I didn't need braces because I essentially stiffened that end of my beams to essentially do the same thing as having those braces. Because to set up all those braces and to bring them in is not the easiest thing to do, and to make sure that they're all set properly to your specimens. So we're going to start out, simplest condition, we're applying just end moment. So the beam has a uniform moment over its entire length. Okay? Linear shear and uniform moment. So as we load this beam, it's going to just deflect downward vertically. It's going to eventually reach a point because there's no other bracing besides at the end, and our unbraced length is L sub B. Okay? And let's say for this particular beam, we don't know what L sub B is, or where is L sub B greater than or less than LR, LP, LPD? We don't know that. So we're making the assumption that as we load this beam, eventually that top flange is going to want to buckle laterally, just sort of like minor axis bending of a plate. I thought you were going to bring some toys. And once it starts to buckle laterally, what does the tension flange want to do? Does the tension flange want to go or want to stay? Tension flange has got force in it, right? It's like pulling on a rope or a rubber band. See, you always should have a rubber band. It doesn't want to move. If I try and move it and let it go, it's going to want to pull back. Okay? So it's trying to restore the beam so the loading stays vertical in the plane of the beam, whereas the top flange wants to go. So this is where we get this lateral movement and the twisting movement of the beam. So where are we? So right now we're going to say we're here. I bet you there's a few more things that come up here. Okay. So where did we get on the curve? We got up to what we're going to call an elastic moment before it laterally torsionally buckled. That could have been drawn up here, could have been drawn here. We're only looking at, this is MP, and we're somewhere less than MP. So our elastic lateral torsional buckling prevents us from achieving any yielding in the cross-section. So how do we determine M sub E? Okay, our elastic moment. And as we move up the curve, and now we're looking at our nominal moment capacity and our end rotation. See, here's that easy way to do it. Same difference. This is half my beam, right? Half a simply supported beam. Cut it in half, right? At where I apply the load, it's like a fixed point, right? We hope it stayed fixed and it didn't move. But you saw, because there was a stiffener there right under the load, because we didn't want to crush the web under that load, there were stiffeners there. But on that one test where all the local buckling was on one side, did you notice that that stiffener wound up looking like this at the end? So we have a nice linear stress distribution. These dotted lines would probably represent the stress at plastic. So we haven't gotten there. Nothing is yielded. It's all elastic behavior. And we can then move up the curve. Let's go back a minute. So this is our ME, okay, in this condition where we've got elastic lateral torsional buckling. So before obtaining the theoretical solution for our elastic moment, we're going to do a parametric analysis. And really, it's just if you had to derive this equation, we'd all leave engineering. Thank goodness there was nothing but paper and pencil at the time that this was done. So what types of terms are expected in our solution? So if we think about lateral buckling, okay, it's really EIY, right? It's the IY of that flange, right? That's what we're really looking at. And a length, okay? And then torsion. We have two types of torsion. Salmon torsion, which is really just the twisting moment, right? And then we have this other little torsion that we call warping torsion. So with salmon torsion, G and J, again over a length. Warping torsion, it's E times a warping constant times, again, over a length. And of course, all of our equations must have pi or else they can't be right. So let's get started. So the equation for minor axis buckling is P sub E. Now this capital E, we're going to say represents Euler. Okay? And that's our famous Euler buckling equation. Elastic buckling, pi squared EI over L squared. And if you see then, we'll change this out in other where we change that from a length to a slenderness. And then we also look at what the effective length is, and we put a K in there. So it's all good stuff that we've learned throughout our careers. So we need to know first the equations for salmon torsion and warping torsion. And the warping torsion is very nicely depicted here, which really is this cross flange bending, okay, which is really a help in our section. Okay, our section, because it's an open cross section, doesn't just want to twist. Those flanges also wind up with a shear force that is a cross flange that's actually providing resistance to the salmon torsion. And to numerically emphasize that point, if I have a closed section, our polar moment of inertia is approximately 4 times the average area of that cross-section squared times its thickness divided by the median circumference. And if we calculate J for this with these values, we get 22.95. So we have a value that we can calculate for this polar moment of inertia. So the GJ, so we know at least half of that. The G is the shear modulus, and the shear modulus is related to the modulus of elasticity, or Young's modulus, by Poisson's ratio. So we know what G is. And for our open wide flange shapes, if you've ever had to do it because it's a built-up shape and you can't look it up, it's just the sum of the 3 plates, so BT cubed over 3. If you ever want to remember, this is a simple formula to remember, BT cubed over 3. So if you have any open cross-section, you can break it up into its individual plates. You can calculate its polar moment of inertia by this equation. So, and we can do it just, if I wanted to check the value that you're given in the manual, when I look up my W8 by 13 and there's a value of J, it's going to come out pretty close to this. All right, so here's the top view looking at warping torsion of what's going on and how do we get this expression for warping torsion, or the cross flange bending to resist the applied torque, because that's what's happening in our lateral torsional buckling. So what is the relationship to rotation? We can take the torque is equal to 2 times the flange shear times h over 2 the moment arm. And with that flange shear, we can take the first derivative of that, right? Shear and moment are related. So V sub f is equal to dmf over dx. And we can write that the flange moment then is minus EIF times d squared w over tx squared. We're really getting heavy into this, and it'll get worse before it gets better. Okay. So we finally, in substituting then for dw into this expression, h over 2 times the first derivative of the rotation, which is curvature, we can then get to this expression. So our torque is now equal to minus EIF times h over 2 times the third derivative of the rotation over dx cubed times the distance between the two flanges, the h. We can also write this relationship of rotation that the torque is equal to, so it's now VF, V sub F times h. And if we know the moment of inertia of the flange, we can also represent as IY divided by 2. So we're looking one flange, right? We already had IY for really for the minor axis, and we can neglect the web when we do that, because the web is a negligible contribution in all of this. So anytime good engineers can take a simplification, take it. Okay? One of the things that I really have to correct people when you say, I've ignored that, please don't ever say that. Say you neglected it, which tells me that you actually evaluated it and it's negligible. It's approximately 0. Okay? But when you said you ignore something, somebody can come back and say to you, well, how do you know that? Did you consider it? So again, we're going to get to this expression for our torque in terms of our warping torsion. It's minus E times CW times the third derivative again of theta x divided by dx cubed. And we're going to start putting this all together. So there's our Saint-Venant torsion, GJ times the first derivative of the rotation. And here's the warping torsion, and notice the minus, so it's a help to our applied torque, is E times CW times the third derivative of a rotation over dx cubed. And so there's our total resisting torque, which is now this expression. Back to our nice picture. Pictures are always good. We see the lateral movement and the twisting movement. And we're still trying to derive the equation for the elastic moment. Okay, because we're going to want to compare that elastic moment to MP. Where are we at on the vertical axis? Okay, we will know, and you get to set L sub B. L sub B is all up to you, and then you need to determine where you're at on the vertical axis. So again, some of our simplifications, theta is small. So that says when I calculate, now I need to calculate these moments. So here we've now taken, there's our moment, right, applied to our undeformed geometry, essentially. But now I'm breaking it up as I'm applying it to the deformed geometry. So I have now an mz prime and an my prime, and I've got to calculate these two parts. So what is the cosine of theta for this? If theta is small, the cosine of theta is 1. Approximately 1. And what's the sine of theta? Sine of theta is just theta. Okay, so we get these two simplifications for these two values. So now my my prime can be reduced, put in terms of m sub e times theta x. And we need to do a little bit more work. Now we're looking in plan that there is the top flange of our beam that's laterally buckled. So if we take a free body diagram of one end of that, there are our end moments, our ME, that we're trying to determine what ME is. We now are going to say that, well, now in that free body diagram, I have this rotation along the length, which we're now calling alpha, which is equal to dW divided by dx. And again, there's our moment, ME, and I'm going to break it up into these components. There's our applied torque. Okay, to get that twist, because this is what I'm really getting. I need to get down to what is this. So again, now alpha is small, even though we always show this big, and in those pictures it was really big. But when we think about it, we are looking at the stability limit of when the beam is thinking about staying straight, up, too much on, and now it's just going to start to move. It is that instantaneous lateral torsional buckling. When you see those pictures at the end, guess what? They were done under load control, right? That Edmonton Bridge buckled, well, actually probably its own self-weight. But the other one it could have buckled when they took the deck off. Remember, if you're ever doing a project a roof, and you've got joists or whatever purlins there on the roof, and you start de-roofing because you're going to rebuild the roof, you're removing what? To the top flange of those beams, or trusses, or joists. So before you go so far, or your contractor goes so far, make sure things will remain stable, because you're releasing that lateral support. So getting back, so our alpha is small, so now we can write this m sub z prime is approximately equal to m sub e, and our torque is now equal to m sub e times alpha, but we defined alpha in terms of dw over dx, so we can plug that in here. And we're building our equation for our applied torque. So T is equal to m sub e times dw dx, which is equal to our Saint Venant torsion and our warping torsion components that we had done before. Now we're going to take the derivative of this expression, because eventually we need to get to a homogeneous differential equation that we can solve. Okay? So we want to get everything in one set of terms. So our first expression for our elastic moment is the second derivative of w over dx, which is equal to this. And now we're into a fourth order differential equation. And we can make one more substitution and get everything in terms of theta, because we had these thetas and this w term. So we wanted to get rid of how do we get this w term out of it? And eventually, in going through this remaining math, we get this expression. And if we do just a little bit more rearranging, we have our homogeneous differential equation here. And if we apply the simplest boundary conditions, remember we started with just a uniform moment. So our simplest loading, we get this expression at the bottom by applying our boundary conditions, no rotations at the ends. Okay? No rotations and no second derivative of the I don't know what that is, the change in curvature at the end is 0. I don't know what else we call that. So there's our sanity check. There's our top flange in compression trying to produce our minor action buckling. And here's our bottom flange in tension resisting this minor axis buckling by creating a resisting torque, which includes both the Saint Venant torsion and the warping torsion. And here's your expression, which you will find in chapter F. And it is the expression for that part of the curve. How much of that part of the curve is valid for us to use is another story. And we go back to the assumptions. We did it with a prismatic member. Only major axis bending occurred before buckling, only linear elastic behavior, only uniform moment distribution, and it's the support conditions. These are the things we're going to look at the end of the presentation. Okay, so this is where we're going to get to, and now I'm going to turn it back to Craig to wrap things up.
Thanks, Barry. All right, so now the fun part comes, right? We've got the basic case covered. Boy, we saw some interesting equations there, and the solution is a whole nother 15 slides that we didn't expose you to. But really, in the real world, we have significant deviations from all these assumptions that we talked about. The first of which, certainly, and probably the most one of the most important, is inelasticity. How do we deal with that? How do we work with the fact that when we start to bend that beam upwards, we may end up in this region, where I have some of that cross section plastifying, right here on the flange tips in this particular, or the flange edges in this particular picture. What does that do to our curve, right? We're still going to have lateral torsional buckling. We're still going to get the twist and the translation, but when we take that load off, we are not going to get that elastic rebound, or the full elastic rebound. So what does that look like on our curve? Well, we define that region of inelastic lateral torsional buckling between two variables, L sub P and L sub R, as Perry mentioned, along our horizontal axis, right? How do we draw these lines? Where do they come from? Well, the first one's the easy one, the L sub r, that separates the inelastic lateral torsional buckling from the elastic torsional buckling. In my mind, that's the easiest one, right? All we're going to do is set that elastic moment equal to 70% of the yield strength times the elastic section modulus with respect to the strong axis, and that 0.7 is a tip of the hat to the fact that we have some residual stresses in the cross section. I will tell you, as my position is Task Group 2 Chair for the Structural Stability Research Council, we're really questioning as to whether we should take that kind of a reduction for modern residual stresses in hot rolled shape. So I would expect over the next 5 years to maybe see some research done on that and maybe even relooking that number. It's always a topic of great conversation. But after we do that, in our current code formulation, we simply solve for the unbraced length, and that becomes our L sub r, right? That's a pretty easy equation that we can all do. Now let's talk about the fun one up here. How do we get to that one? Well, first, you don't ignore the uniform torsion, GJ component, but it's really insignificant compared to the warping torsion component of the resistance up near the plastic range, right? So we're going to set that GJ equal to 0 in our elastic equation. We're going to set our ME equal to MP, and that equals ZXFY. We're going to make a couple of other assumptions, and we're going to come up with a limit, and we're going to look at that limit. We're going to compare it to experimental results, and we're going to say, well, really to achieve the rotation capacity Perry talked about in his brief, we really need to use the experimental results to come up with our final equation for L sub P. And you can all take a big breath that we're not going to go through all the equations that led us to that conclusion, right? So the ultimate conclusion is that the line that we draw between these 2 points to define the inelastic lateral torsional buckling region, sure, it's anchored in the appropriate equations down here, and then it's really experimentally derived on up to this point here. Now, it is backed up with equations, and we're not violating physics or anything like that. But really, that's how we come up with this. In class, I love to get up there and just do a bunch of dots. Here are all our tests. We draw a line through them, and that's where we come up with this region. Okay, so more empirical than theoretical. But that defines our region. So we clean things up. That leaves us with our final AISC curve. So that's how we deal with only linear inelastic behavior. We basically do a linear interpolation between the full plastic moment capacity in L sub P and our elastic buckling equation in L sub R. Now let's talk about only uniform moment distribution loading and those load conditions in the deviations from the basic case. First, our basic case. Remember, as Perry had mentioned, we have uniform moment. What does that moment diagram look like? If you'll notice, we have the same moment all along the cross-section. And really, what does that mean when you think about it in terms of the cross-section itself? We have uniform compression across the top of that compression flange. Well, if we change our load condition to distributed load, a very common load, what's our moment diagram look like now? Now it looks like a parabolic moment distribution, to where now, if we think about that compression flange, out here at the ends, we have much less compression in the flange than we do right here in the center region. Here we're fully stressing that compression flange. Down here, we're not really utilizing all of the capacity of that compression flange. And then finally, even more informative loading pattern, just the single concentrated load. Now we even have less. We're using less of that compression flange capacity here between these curves. So how do we account for that? Clearly, the Timoshenko solution with the uniform moment is the worst case. So we can actually use that to our advantage when required. The code allows us to do that through this equation. I've grown up with this equation. Didn't even realize there were other equations for C sub B that we'll talk about here until I got involved with SSRC and realized that this equation really is, it's a robust equation and a good one to use. But it really works very well for a parabolic moment diagram, right? And if you have straight lines between these points, there's another equation in the code that will allow you to be a little bit more efficient for that really specific kind of loading condition, right? So we'll all remember this formula. We've got to find the maximum moment, multiply by 12.5, and then divide by 2.5 times that maximum moment, and then take these quarter point moments, multiply by 3, 4, and 3. And we're taking the absolute value of these moments, right? Common error is to think, well, if I have some kind of reverse curvature, I've got to take the negative value down here. Nope, you're using the absolute value of the moments to figure out this C sub B. Yes, yeah, and we're going to bring that point up. This is between the point of bracing, right? Where we look at the segment, the unbraced length, between the points of the braces, not between the points of inflection. So what does that do for us? Where does that show up? Well, our basic case has that C sub B equal to 1, that uniform moment loading condition. If we have a point load, let's say, and we get a C sub B greater than 1 using our formula, then our curve looks something like this. We're simply just multiplying these values by C sub B, but there's one very important caveat to this. Obviously, our equations here, we're going to include in the code that C sub B times the inelastic lateral torsional buckling strength times the critical elastic buckling stress here to get that multiplier of C sub B. And what does that look like in our curve? Well, if we happen to have some bracing provided or a link between our support points, it falls a little bit less than L sub P, so we're in that inelastic range. We calculate our C sub B, and it turns out that we get a value of Mn above our MP. Should we use that value in just normal design, not in Perry's experiments in his displacement controlled? Generally, no. We don't want to use that. We obviously have to drag that back down and say, okay, yep, we've got to make sure that we do not use our, do not go above the full plastic moment capacity of the cross section. So this is when my undergraduate students, I could always catch them on that. I would hammer that home, and then of course on the exam they would forget and come up with a nominal moment greater than the plastic moment capacity. Well, a couple of specific conditions that we might run across. There are other formulations of C sub B in the appendix, the commentary to F1 in the code, and those have been more recently added over the years. Here's a great example of one. If we do have reverse curvature, and the example is a top flange braced and in tension, the bottom flange unbraced and in compression in some regions here you'll see in the beam, well, we can use this formulation for C sub B and get a more accurate result. And what we don't want to do is say, oh, there's my unbraced length, right here, right? We want to make sure that we get our unbraced length all the way out to the points of the bracing, okay? And then we can use this and get a more accurate value of C sub B for this particular moment diagram. Another common case that you may see is uplift. If you're doing some kind of roof uplift calculations for wind, you may see this. And there are a couple of a few different cases of C sub B that you can use to get a really good estimate of your C sub B again. And then there are other conditions in commentary F1. So just don't think that you're limited to just the single formulation of C sub B. If you're really needing to get the accurate and extra calculated moment strength out of your cross section, then certainly turn to C sub B. Next, and probably the funnest part here, is let's look at our final assumption down here of free to warp, right? What happens if we actually provide some resistance to warping at the end? And just as kind of a physical feel, if you don't have a physical feel for what warping is, if you just pretend your two hands are the ends of the flanges and you simply twist one opposite of the other, that's what's happening. If you can extend that out in your mind, you can see the top flange bending this way, the bottom flange bending in the opposite direction. That's a qualitative feel for what warping is. So how do we stop that? Or how do we actually provide warping end restraint? Here's that slide that Perry showed. There's the example of warping. Well, we could put some device, perhaps a tube, between those two flanges. If one flange wants to rotate in its strong plane one way and the other wants to go the other way, why not tie the two of them together? So they literally brace one against the other, right? So this is going to help us stiffen the girder against lateral torsional buckling. And what we're really doing is changing that free to warp end condition. This has been done in some bridge applications already. This goes back to research that was actually conducted for the building industry back in the mid-70s, in 1977. And back in 1977, they found that you could get a 30 to 70% increase in elastic buckling capacity using such devices. Now, my guess is it really didn't take off in the building industry, because in the building industry, we're typically not just working in the elastic range. But in the bridge industry during erection, we certainly are keeping our girder stresses down in the elastic range according to AASHTO. So it seems to have taken off a little bit more in the bridge industry than the building industry. So why use a closed tube? Are there other things? There are other things we can use, and we'll talk about those briefly. But what does the closed tube offer? It offers a very large torsional constant. Right? We go back to that slide that Perry showed. 22.95 inches to the fourth is a torsional constant for this closed shape. If you notice on his slide, for the open wide flange shape, the torsional constant was down around 4, right? So open shapes are very inefficient in torsion. Closed shapes are very efficient. And that's what we rely on for our tube-shaped warping restraint. So we have gone in the lab and tested these devices. Here's an example of one test setup. And yes, I was the lucky one. I got to do elastic tests. Perry had to do the plastic tests, so I could do as many experiments as I wanted, and my instrumentation didn't pop off of my specimens. But if we look at an example of a couple of W30 by 90s with a gravity load simulator here, so we don't have any restoring force applied to the beam as we pull down on this beam. If we don't have a pipe stiffener on the end, we get this kind of load versus lateral deflection curve. If we put a warping restraint device in, the pipe stiffeners at the ends, we get 130% more capacity before we start to see the onset of lateral torsional buckling. All right, so it's quite a significant increase. So how do we predict the increase in elastic buckling strength, right? We're talking P's and lateral deflections here. How does that translate into actual strength? Well, we start with our basic elastic buckling equation. And really what we're trying to attack now is the effectiveness of the warping torsion component here. We'll recognize this, and this equation is over here. So we're impacting the boundary condition, which really is going to affect the unbraced length for torsion. And we can affect that much like we do with a column that's in pure compression. We can put an effective length factor for warping on that particular unbraced length in that portion of the equation. So then, now it's just back to our undergraduate days of using the side sway inhibited chart for columns, right? But we've got to calculate some G values to try to figure out that K sub W. How do we get the G values? Well, we remember what G is in its basic form. It's the ratio of the supported member stiffness to the supporting member stiffness. Well, what's our supported member? Well, we're trying to support that compression flange. What's our supporting member? Well, it's that torsional stiffness of that pipe over half the pipe height, because our point of zero twist here between the flanges is close to D over 2. So we'll use that value as our supporting stiffness. And if we take those values, are very easily calculable from the cross sections that we have, and we plot those G values at each end of the beam, plot one side, plot the other, and draw the line across as we normally do, you'll come up with your K sub W. Right? And then you can insert that K sub W right into the L sub B for the warping torsion component. Now, that's not the only shape. These warp devices have been looked at over the years. These two references that we'll show you also at the end, the guide to stability design criteria for metal structures, you can go inquire and look at this actually down at the SSRC booth right next to the AISC booth. And it will explain this warping devices to you. And if you want to dig even further deeper into the AISC literature, you can find some of these other shapes. One example is just an end plate connection. And there you can see we can calculate our G value for that end plate just by GJ of the plate over the depth of the plate as well. So many more formulations, box stiffeners and other kind of stiffeners that are involved. And one perhaps area that you may not have considered if you're working with continuous beams is the fact that adjacent segments that aren't the critical segment, i.e. not the ones that are going to buckle first, also brace the critical segment here, right? And they do it two ways, right? Not only do they provide that warping restraint, much like a warping device, but they also provide lateral restraint, keeping the top flange from wanting to buckle laterally out as well. So you kind of get double the bang for your buck there. Of course, the question is, how do we calculate that increase in strength? Well, There is a way to do that, and the current edition of the code in the commentary actually points to the SSRC guide that explains the process. Here it is quickly summarized for you. You basically need your moment diagram. You got to identify your critical segment, right? That's something that you always would have to do anyway. Then you have to calculate the stiffness of each segment, right? For the critical segment, you're going to get the lateral stiffness there. And then you're going to calculate the stiffness for the adjacent segments, accounting for the end conditions. The value of n is going to be 2, 3, or 4, depending on whether you have a continuous or pinned or fixed boundary conditions at the far end of your adjacent segments. You'll have to calculate P. That's a little bit extra analysis. You'll have to calculate P, the vertical load that you would have to apply to those segments to actually get them to buckle. And this is a measure of how much left does that adjacent segment have to give to the critical segment. And then, again, you're going to determine your G value, and you're going to use your side sway inhibited chart, not only for K sub Z, or that K sub W, as I called it in the last slide, that warping torsion effective length factor, but you can also use that K value on the other unbraced lengths, or the lateral translate, or the lateral buckling unbraced length in Timoshenko's equation as well. So you can use that reduction factor in both. So there they are. That's how you would modify your equation. You get that K sub Z here and that K sub Y there. And this procedure, and there's an example problem in the guide to stability design criteria for metal structures for you to follow and consider for your use. Finally, what does that do for us on our curve? Well, if we're sitting out here with an unbraced length there, what this is going to do is allow us to slide back to have an unbraced length a little bit less than that, right, and increase our elastic buckling capacity. So increases of about 30% is what we've seen are possible. You have a couple of cautions, though. You want to make sure your material remains elastic. This is an elastic buckling solution, not an inelastic buckling solution. So you want to do really make sure it remains elastic. That's why this is primarily helpful during girder erection and those sorts of things. Typically, after your structure is completely finished and decks are in place and that sort of thing, we're not really worried about the elastic capacity anymore. But then also, you have to ensure your braces are properly designed. All right. Again, because we're increasing the stress in the member, we're increasing the requirements that we're putting on our braces as well. All right, we're down to it. Summary and final thoughts. First, this has really just been kind of a quick survey over a couple of the more interesting sections and derivations from the basic case, right? So where else can you go for more help? Well, obviously read that steel construction manual. It has a lot of information in it, and especially back in that commentary. AISC runs a series of night school. Often they run stability in their night school. You can always get a hold of the AISC Solution Center. You'll ask a question, they'll probably email Professor Galambos for the answer. But you can go to the Solution Center. You can go to the Stability Short Course. Ron Zemian gave that this time. It probably will be offered again next year as a part of this conference. So if you want to learn more there, sounds like we had a couple of folks that are in the audience. You may want to speak to them about it. Structural Stability Research Council Annual Stability Conference and Proceedings. The SSRC Annual Stability Conference runs along with this conference, so if you see an interesting topic there, or you can go as an AISC member and download the proceedings and read more about the most current research that's going on in this area. And then finally, the Guide to Stability Design Criteria for Metal Structures has just a plethora of information on these topics. And you're going to see a lot of other different topics we didn't talk about today, primarily things like load height effects. You know, what happens if I load the top flange as opposed to the shear center as opposed to the bottom flange? Does that help or hurt me? In terms of moment strength, you know, singly symmetric shapes other than I shapes, and of course bracing design, and on and on. So, and just a few of the references that we used in this presentation here. A couple of pages of references. All right. With that, let me again announce that our PDH code is 14624. Got it right on the last slide, which means Perry gave it to me right. I just typed the wrong one in on the first slide. And with that, I think we do have just a few minutes for questions, about 7 minutes before 9:30. So Perry and I would be happy to take any questions you might have.
Thank you for you all sticking around through that. Better than going back to school. Any questions? Yes, sir.
All these LTD assumptions are based on the constant IY, but in a bridge curve, that's not the case. And I forget if it's Asheville or AISC or both, but when they present the equation for CB, it's a constant IY. Is there an easy approach you can take, maybe taking a smaller section across the whole length and treating it as conservative as opposed to calculating CBs, or is there a different approach that we should be taking for that CB for these?
First, you're going to start with a CB of 1 and say, am I okay?
Yeah, we had a case where that wasn't okay.
So then I start to say, okay, if I do that, I mean, it's really now, you can come up with a reasonable, rational method of calculating a C sub B for your type of condition and looking at these other methods that are in the commentary. I mean, I think that's what you put on your calculation and it gets reviewed. And if it's rational and reasonable, I think it would be fun. Okay, you have some limits. Okay.
As long as you're not assuming.
Right. And you know, in this world of CNC machinery, and I was down in Colombia a couple of years ago, Colombia, South America, and they were making all of their eye sections were all made out of plate or coil. And there were 3 coils coming into this machine that were putting them together. And I'm thinking that I could either vary the thicknesses of my plates, which is very easy with the plate girder, but I could profile the thickness of my flange along the length, or I could profile the width of that member. And it's all things that we can do today with the machinery that we have, that we don't have to live within that box of, it's a doubly symmetric eye section. So, I mean, I see these things coming to optimize sections as long as the cost to manufacture or fabricate doesn't wipe out everything you're trying to save by your optimization. And then also looking at how is it going to be out in the field to a wreck. You know, that's really your big price tag. So what you're saving up front to try and do this good stuff, at the end of the day, you know, may wind up costing you more with the erectors because they don't have handling.
Yeah, and I can understand the AASHTO consideration for, you know, saying let's not worry about C sub B with this varying cross section, because C sub B is a function of the moment diagram, and if you have different cross sections along the length, trying to apply one C sub B to that cross section would be very, very problematic. So my guess is, and I'm not real familiar with the provision you're talking about, is they're just trying to be conservative and simple until you just leave it at 1. But again, if there's a rational analysis, if the code allows a rational analysis. Mm-hmm. Yeah. Mm-hmm. Yep. Right.
The CB equation in the manual, where I simply supported the beam of the moment gradient, the assumption is that the ends of that beam are braced. What constitutes bracing? Does a stiffener work? What does that bracing have to look like?
I would say if you have end stiffeners welded in there, that would work, which was in my experiment. And I do not, yeah, so there should be something there. And again, it's where is the load? I mean, a lot of what we do in our concept is the load really on the top flange. You know, when we do a lot of this, we always think about that it's the neutral axis that I'm loading, right? Or is the load being hung from the bottom flange? You know, so there are those things too that really come into play.
We had worked for a lift company and we used a lot of gantries for better reasons. And we used the beams to support on the gantry, so the bottom flange is clamped to that gantry, but the top flange is not braced. But most of the time the load is hanging from the low, so it wants to come back to center. So how do you determine whether CB is appropriate or not?
Oh, that's a great question. Yeah, load height effects. And so there's been some research done by Todd Helwig and others that have shown a very simple way is just to use a modifier of 1.4. And the SSRC guide goes through that procedure in detail. It's just a matter of whether that 1.4 is dividing C sub B or multiplying C sub B, right? And that's where you're talking about whether it's helping or hurting your the cross sections want to twist, right? So yeah, I would really recommend that you look in Chapter 5 of the SSRC guide, and it'll explain to you how to account for load height effects.
Thank you for your attention.